Alright, time for another draftphysics.com, debatephysics.com, also video presentation. And one of the people who are very cowardly cowards who won't do the debating thing is this Professor Dave. So he has also, like all of them, made an entropy video, and he just says the same crap. I mean, he adds some other features, but it's just the same bottom line crap that somehow they know the universe is falling apart. And they know it for, like, not because the evidence says so, just because they wrote a law, a piece of dogma, and they just think the dogma is somehow a universal principle because they have one analogy. And yeah, there's plenty of analogies demonstrating exactly the opposite principle, and they just couldn't care less. But anyway, so some history. I mean, I have tried to get Professor Dave to play along. He's one of these debunkers to some extent. Does a lot of different kinds of videos, frankly. And, you know, his recent ones aren't very well viewed compared to his older ones. So this is a couple of years old, this entropy video. And so it has a couple of million views. But his more recent videos are stuck with a less impressive numbers. Now, he did things I was supposed to say on the Pierce Morgan, so that one got 511,000 views, but the video before it 5,000, the video after it 9,000. So very uneven in terms of the interest of his followers. So the Terrence Howard 700,000. So whatever this, this whole idea of putting some stupid actor, giving them celebrity as a physicist because they can say some crap. I mean, and this is what entertains people. It's pretty sad, frankly. The science isn't all that important to them. So the more science in the video, the less interest seems to be pretty much, the standard. 858,000 views for debunking a flat earther. Ooh. Yeah. It's just pretty pathetic. Anyway, so yeah, I think the one video does have a funny cow update on stubborn Ashmod, the whiny coward. So yes, you shouldn't. That's whatever. Pothead calling pothead, stoned. Um, forget it. Too silly. Anyway, so let's go to the video. And I guess I better make sure the volume settings are correct. I believe that's right.
Knows a lot about the science stuff, Professor Dave explains.
The laws of thermodynamics help us understand why energy flows in certain directions.
So the laws don't really help you understand anything. They're dogmatic declarations about the truth. And the first law of thermodynamics is really so old and so already stated in so many other ways that it's not really saying anything new, so it shouldn't even be called the first law of thermodynamics. The idea that energy is conserved was already stated by people like Descartes and Newton and so on, even Leibniz. So it wasn't something new. De Chatelet didn't invent the concept. It's a really old statement about reality.
And in certain ways. A lot of the concepts described by thermodynamics seem like common sense, but there is a layer of math beneath.
So it really doesn't. None of the other two laws make any sense at all, as I'll demonstrate. So it's just contrived babble, and here's the dogmatic, we will present it in a creationist documentary where we'll only show you the pieces of evidence that point in our direction, and we won't show you any of the evidence that points in some other direction. Clearly just crap as science.
The intuitive level that makes them very powerful at describing systems and making predictions.
So again, very unpowerful at doing any of that, because you could do all of that without these laws. So these laws won't help you really. It's just simple understanding that, the more pressure you put on a piece of glass, let's say, there's a point where you can realize, well, the glass is likely to crack. And it's only that it's likely. You won't be able to predict exactly when, because the exactly when is dependent on the fact that the glass has a defect in it somewhere.
We won't get into the math, but we should be able to
So the math really doesn't do anything but vague. Okay, so it's almost, look, it's like, you can play games with the whole idea of mathematics that helps you understand a curve or something else, but you can also just draw a picture of it. You can mechanically know by just drawing it. You want to know what angle creates what section of an area. Well, guess what? You can just draw it, okay, and then just measure it, and you'll find out it's 38%. So, you don't need calculus. You can do it other ways. Calculus is just a more expedient, in some circumstances, more expedient. Depending on how jiggly the line is and how precise the answer you need is, again, it might just be easier to draw the line.
describe these laws conceptually. The first law, described in the most basic way, highlights conservation of energy. Energy is not created or destroyed.
All right, so right there, they're already in violation, because as I pointed out, the gravity thing, oh yeah, that's tricky, isn't it? Because guess what? It is actually producing momentum in objects. You actually have momentum into the Earth. You're adding pressure to the center of the Earth right now, and that energy will be dissipated as some sort of form of real energy. That is, it's not going to be dissipated as anti-gravity. It's going to be dissipated as photons, some sort of radiation. So right there, you're creating energy in the universe technically, because you didn't use a photon to push me in, and you produced a photon out. So if their science had any consistency, they'd have to recognize that unless they make gravity a real force, they're just talking out of their butts to make claims about any kind of energy consistency.
It only changes forms, from potential energy to kinetic energy.
So there's no such thing as potential energy. There's a boat on the side of the Mississippi River. Where's the potential energy? There isn't any potential energy. There's a kinetic active stream, and you're just going to stick your finger in it, so to speak. And the same thing happens with gravity. It's an active stream, all right, and all you can do is place something in the water and watch it flow. That's exactly how Leonard Susskind teaches relativity, by the way, is to analogize it to a stream of water.
Energy to heat energy, etc.
So heat is momentum. It's movement of matter. That's always momentum. Anytime matter's moving, it's momentum. That's it. That's all there is in the universe is momentum. There is no kinetic energy, 1/2 mv squared. Fable, just a fable, just a religious concept.
While we have found this to be untrue on the quantum level,
So whatever that even means, yeah, the quantum level, because, well, we can't find anything because everything's Heisenberg, and we can't measure anything, so yeah, we can't do any physics on the quantum level. It's all wooey down there.
for chemists, it does just fine.
So yes, and that's basically what this guy is, I guess. His primary subjects do seem more related to chemistry and biology than physics.
However, there seems to be a preferred direction in which energy flows from one form to another.
So this is kind of a lame statement, okay? Either it's a, well, anyway, he's prefacing the second law, and this idea that he says there's this preferred way, when the preferred way in space is that I put something in space and what happens to it? Well, it figures out which way is more gravitational mass is closest to it. So whichever way, you can't put something in space and it doesn't move, because the fact is it's going to be in a field of gravity created by the entire universe that is going to have a bias in a direction, and it will start drifting in that direction. That's the reality. Okay, so, this bullshit.
In order to understand why, we look at the second law.
So, and the second law is just a law. You're not going to understand why it's a second law until you view the universe and say what's really happening. Are stars all falling apart and none are ever being made? Is that what's happening in the universe? I mean, what's the argument? If you're going to state, that this phenomenon of everything breaks but nothing ever is created, it's just not factually true. And then again, if I was to use analogies, okay, I could say that two magnets prove the case, okay, in the sense that I can have two magnets separated from each other, that is higher entropy, and then they smash together, okay, through I didn't have to do anything. I had to just let go. And now they're really hard to take apart. So it's exactly the opposite of entropy in the sense that there's no easy way to take them apart, and it was really easy to put them together. I'm saying that gravity is essentially the same as that, okay? Once you smash the Earth into a ball, it's really hard to pull pieces off, right? They made that whole Interstellar movie about this concept that, it takes this magical, we have to find this magical theory that will allow us to send our giant cement tower to Saturn, because gravity is going to stop us from doing it. Because it doesn't like to be entropic. It doesn't like the universe to have entropy. It's stopping the entropy. Hilarious. I mean, it's just so obviously silly to assert this principle as if it's universal when it clearly isn't universal.
The second law introduces a new concept, entropy. Entropy is quite difficult to understand, but we can most easily...
So I don't even know why he would say it's quite difficult to understand, because you either understand it as being, stuff being separated, stuff being, the opposite of a convergence, a divergence. Lots of ways to understand it, or a mixing. You can talk about things being mixed. Okay, now that doesn't seem to be a reasonable definition of entropy, because the mixing doesn't matter how mixed it is. Mixed is mixed. They're occupying the same space, whether I have them red, black, all in order, or they're all mixed up. Who cares? I mean, it's not really the same concept, right? We're just talking about, with energy, it's just about whether the energy is in this small space or whether the energy's spread out in a bunch of tiny little bits over a very large space.
Describe entropy as disorder. And the second law states that the sum of the entropies of a system and its surroundings must always increase.
So it doesn't. So it's just obvious that it doesn't in this universe. So he rewrote it as the entropy of the universe is always increasing. Like the universe is getting more scattered. And again, the obvious feature of the universe, the biggest feature, the feature that runs the whole thing, frankly, there isn't any real universe without it, is gravity. So it's just a nonsense statement, a complete rejection of anything that can be rationally deduced by looking at the universe. Now, let's understand, this was written by people who didn't have a very good view of the universe, but they still knew what gravity was. And, to deny the existence of gravity is silly. I mean, that's flat Earth.
In other words, the entropy or the disorder of the universe is always increasing.
So it isn't. It's not a fact. You have no evidence that more suns are dying than suns being created. There's no evidence that the energy produced by any body in the universe doesn't go somewhere and make something clumpy again. So the whole argument is that the universe is made out of what you could call, batteries, and you're either discharging or charging. And the fact is, every time you discharge, the energy eventually is going to charge another battery. That's the more accurate description of the reality. Entropy, for humans, we deal with machines and devices that we have created that aren't indestructible. They are fragile. They're not perfect. We don't make something like a cannonball out of titanium or something. So we make very few things, okay, that can't do anything because they're so simple and uncomplicated. We make complicated things, and complicated things have weaknesses. And the fact that it's easier to break something than it is to make something in our world doesn't mean the universe has got the same problem. It's really easy for the universe to smash two magnets together. Really easy. And it's really hard for the universe, without fingers, to pull them apart again.
Within a system, there is also a tendency to go towards higher entropy.
So again, whatever this even means. So the universe does it, systems do it, and the argument is no, there's plenty of systems I can describe where that's not happening. It's exactly the opposite is happening. Storage is happening.
The classic analogy is that your bedroom will over time become messy, but it won't suddenly become neat.
Right, so it's just a silly analogy, and he uses the word spontaneous, which I don't even know why a scientist would use the word spontaneous, because we know nothing happens spontaneously. There's always a cause to the effect, and nothing is triggered without the trigger being, put in the trigger position. And so there's always a cause to the effect, and nothing happens on its own initiative, or whatever you want to say. It just doesn't. It has to be triggered.
Another way to look at this is to say that entropy is a measure of how dispersed the energy of the system is amongst the ways that system can contain energy.
So again, it really doesn't matter, frankly, whether or not you've mixed it or not mixed it, as long as you've spread it out. So that, I think, is two separate subjects, and the very fact that they've mixed these two subjects is also part of the fraud.
Yet another way is to analogize entropic states to computer code.
So, yes, and again, I'll just analogize it to a magnet and say a magnet is like gravity. And you're already way out of luck in talking about the fact that it's somehow easier to break it apart than it is to put it together.
Take, for example, an ionic solid compared to the same substance as a liquid.
So this was a preposterously silly analogy, frankly. It's just on its face so dopey, because he's going to go by the amount of information that's in the two things and try to imply that there's more information in the constructed solid than there is in the liquid, when it's exactly the opposite. The amount of information you need to detail what the hell's going on in the liquid would be volumes, because of the fact that everything's moving and moving a lot, and everything's banging into each other. So it's a huge amount of information, where the solid, there's a little jiggling, but there's not much to track. So it's a lot easier, a lot less information is in the ordered solid than is in the disordered liquid.
Clearly, the solid state is more ordered and the liquid state is more disordered or higher in entropy. To describe the solid state using...
So that's of course true, right? But it doesn't have anything to do with information.
Computer code, you would need to include terms that describe the geometry of the lattice, the intermolecular distances, the precise configuration of every molecule, and...
Right, so if you have to do that for this, you have to do it for the other things. So it's going to be even harder to do, because all of this thing is all mixed up and all over the place. These are all mathematically rigorous. It's almost like you don't even have to do the calculation, because once you know these three, you know this four. It's going to be so much easier. You can break that down to a formula. There's no formula that's going to tell you the liquid's condition. There's a formula to tell you exactly where everything is in that.
and many other things. But to describe the liquid state, you would need to simply describe the volume of liquid and the shape of the vessel.
Too ridiculous, right? Why? You just changed all the rules of what you're trying to do. So why would I have, if I can do the Reader's Digest version for the liquid, why can't I do the Reader's Digest version for the crystal? I mean, that's just silly.
Because the motion and configuration of the molecules are random. That's far less.
So randomized, okay. So these are words you really shouldn't be using. Random and spontaneous are not scientific, in my opinion, scientific concepts. They're like saying Holy Ghost or something. The Holy Ghost did it. You know, Holy Ghostism. No, there's no Holy Ghostism.
Information that needs encoding, which is a way of rationalizing why increasing the entropy of a system.
So he uses the right word, rationalizing, because that's all this is. This is just contriving bullshit to defend something that's nonsense.
Is thermodynamically favorable.
So again, thermodynamically favorable. He's saying that somehow the liquid state is the more preferential state, when no, it isn't. The state of a material is completely dependent on the temperature, and there's no preferable state. I just lower the temperature, it pops right into the state. I raise the temperature, it pops right into the state. It's just bullshit to say there's a preferable state. And frankly, the more I take away influences, the default is the simpler state, the state you're claiming to have less entropy. That's the default state. 0 Kelvin, I'm going to be in essentially that state. Now, that state's not going to have any non-energy. So again, that's another part where they forget about gravity. Even if I make it very cold, I haven't eliminated gravity, so the substance itself can't be frozen, okay, because it's being screwed with by gravity. There's still pressure in the substance created by gravity.
You can look at all kinds of processes to highlight entropic influence. Heat will flow from a hot...
You see, the real catch of this is, if you take this science to a better level, the real catch is that gravity is charge. It's the stuff holding the atom together. Charge is the real thing in the universe, and it looks like gravity when it's big things. And it's charge when it's little things.
Coffee cup into the table or your hand, because the heat energy will be more disordered if more dispersed.
So the fact that it's disordered again, and I can do the same thing. I can put a little thermocouple next to the coffee cup, and I can collect the energy and pump it right into a battery. I can put one of those little, those little heat engines on there. I can do lots of things to collect the energy in a less dispersed manner. I can convert it really easily.
This is why heat spontaneously flows.
So it doesn't spontaneously. You can't. Why are you saying spontaneous? You're a scientist. You know nothing does anything spontaneously. It has to have a condition conducive to whatever it is you're saying is going to take place. You can't just spontaneously do it.
Flows from hot to cold, and not the other way around.
And the only reason that is to say movement spreads to things that aren't moving. Well, duh. That's not at all miraculous.
Entropy. The third law.
And the funny part is again, gravity is showing you exactly the opposite happening. It's taking moving things and turning it into something that isn't moving much.
Law states that a perfectly crystalline solid.
So the third law is so obtuse, can't mean anything. All right, let's just say, so I don't even know why they bother with perfectly crystalline, right? Because it should be any solid, frankly. Whether it's a crystal or not shouldn't make much difference. But anyway, at absolute zero has entropy of 0. So the trick there is gravity. So let's say I can find some place in the darkest part of space where there's 0 temperature. That is, the thermometer See, the trick is the thermometer still being affected by gravity too. So, it's going to create some sort of thermal energy because it's creating it's the energy of what's holding the electrons and protons and the atoms to each other. The energy bonding them together is created by the field outside. So this whole idea that you can find some place where that doesn't exist, I'm arguing is there's no such place. So gravity always creates temperature. So there is no such thing as absolute zero because there's no place you can go where gravity can't get to you.
At absolute zero has an entropy of zero, as this is the most ordered state the substance can be in.
So again, and it would be it would convert the substance into disorder because the only thing holding it together, you have to understand, is a force. And if you eliminate all force, then there's nothing attracting protons to electrons and nothing causing repulsion and nothing causing motion.
Entropy is measured in joules per Kelvin. Note that entropy is not a measure of energy itself, but of how energy is distributed within a system.
And it doesn't really mean anything. It's a vague concept of having any meaning at all. And so it only can be applied when you have certain circumstances that you're trying to analyze. So, I don't know how to make a quick analogy, but beans in a jar, and then you decide to make different colored beans, like jelly beans, all the same, and then jelly beans of different colors. And yeah, there'd be a different way you could analogize or understand the probability of pouring out 4 blue ones or something. But that's very different than analyzing more complicated systems like even a cup of tea.
It is enthalpy, the thermodynamic quantity.
So that's so queer, a word that, forget it, I'm not even going to pay any attention. That's right, that's too weird.
We learned about before that is more accurately describing the energy of a system. As we will see, enthalpy and entropy intricately relate to tell us something about the Gibbs free energy of a system.
Right, so this is just more crap made up about crap. So it's just double crap. It's a crap sandwich. It's just, forget it.
G, or Gibbs free energy, tells us whether a process will be spontaneous or not.
So it really doesn't. I bet they have no real success in using any of this nonsense to do anything real beyond what you could already know. That, something like gasoline is more ignitable at higher temperatures or something. You can already figure that out. So let's skip all this Gibbs crap. Boring, boring, boring. Okay.
There are those who incorrectly use entropy and the second law of thermodynamics to imply that order can't happen spontaneously.
All right, and nothing can happen spontaneously. God damn it. Why would somebody say that order can't happen spontaneously? Why would somebody say? It's just so unscientific to call it spontaneous. You know that if you're going to cause a battery to be charged, it can't spontaneously charge. No, you have to create a circumstance that forces it to be charged. So, it's never going to spontaneously charge. So I don't know why he's using that word. So we know that gravity does whatever it does without anybody having to hit the switch. So we know we don't need to turn it on, or we don't need to do anything. So if you want to say that's spontaneous because nobody had to hit the switch, the on switch, it happened without hitting the on switch. Well, yeah, and it charges batteries. It charges matter. It clumps it.
But we just showed that entropically unfavorable processes can be spontaneous at lower temperatures if they are energetically favorable.
So again, low temperatures that have energy. So again, it doesn't make much sense, right? No, it doesn't make any sense.
An example of this is soap. You need
So this won't have anything to do with temperature. So he just said something, and then he says this is an example of something at a low temperature with energy. When no, it's really not.
soap to wash non-polar dirt and grime off.
So this is nice. I mean, it's a nice little explanation of soap. The big molecules grabbing little molecules.
Off your hands because they are immiscible with polar water molecules. But soap molecules have polar heads and long non-polar tails, which allows them to spontaneously form structures.
So spontaneously again, I mean, we know it's not going to be spontaneous, whatever that is. We know it's going to be circumstantial. And so the circumstances are either conducive or not conducive. And here the conducive circumstance is the water. The water creates a medium where the molecules can move around and bang into each other and find a more comfortable way to combine with each other. And so the water just helps turn the soap into a configuration that's more likely to trap dirt. So you need the bubbles, essentially. The bubbles help.
Structures called micelles. These are spheres where the soap molecules orient themselves with the polar head.
So I guess, he's saying they're spheres, but, you'd have to argue, well, spheres wouldn't really work, right? Because then how does the dirt get on the inside? It's a little tricky, right? So I guess we don't have a good picture of this entirely, but I would imagine, I guess dirt can push through the outside and end up stuck on the inside. But the idea would be, it's like any protein, it's sticky. That's the simplest way to say it is it traps or makes stuff stick. So like a jellyfish and its tentacles, it's just it's good at collecting shit.
Heads facing out in order to maximize ion-dipole interactions with water molecules that bring the system to a lower energy. And the non-polar.
So again, the system to a lower energy. So so the soap gets hot because it's excreting energy. I don't know. I never heard of that. That by pouring soap into water, I make the water hot. Haven't heard that.
Tails will all face in, trapping the dirt by making a network of van der Waals interactions. The dirt trapped in the micelles washes away because the micelle as a whole is water soluble due to the polar heads facing out.
And water soluble means it sticks to the water.
That's how soap works. And that's also how highly ordered structures can form spontaneously if.
So, okay, it's not spontaneous, and it's just such a wrong word to use in a cause and effect world, and where it's always circumstantial. Again, the glass cracking, it's always circumstantial. It always depends on some weak link, some point where it will happen first.
By enthalpically favorable or energy storing processes. In this way, systems can defy entropy on the small scale.
Right, now here comes the big line. Okay, this is, you're just saying, okay, fine. So you're saying the little universe, or this whatever scale you're saying, there are events like magnets sticking to each other that are non-consistent with the second law. And then my only argument after that has to be, well, aren't there systems in the big universe that are also inconsistent with the second law? And yes, the answer is yes, there are. It's called gravity. And it's huge. The universe has a lot of it.
But the second law does hold true in that the entropy of the universe is always increasing.
So that's it, and that's all. He just says it. So he doesn't have he didn't diagram anything about the universe, didn't show us a picture of the universe falling apart, didn't show us the pictures of, how all the suns fall apart and they're all dying and all the energy in the universe is dissipating into little mushy bits. Didn't show us any of that. Because it doesn't fucking happen. So I'll just play it again. Because it's such bullshit.
Can defy entropy on the small scale. But the second law does hold true in that the entropy of the universe is always increasing.
Bullshit.
Let's check comprehension.
Check contract. So he does a formula he didn't do in the video, where he's pretending they're getting some great number here that tells them exactly how much something or other they got. But whatever, it's really not all that. And so that's it, I think.
Thanks for watching, guys. Subscribe to my channel for more tutorials.
Yeah, really, whatever. No, I won't do that. Anyway, so, so he'll debate a flat earther. He'll talk to religious kooks. But if you want to argue physics, their physics, he ain't going to do that. He won't play that. So you're not allowed to challenge his beliefs. He'll challenge somebody else's beliefs, but he won't let somebody challenge his dogma, his religion, his creationism, his theory of reality. Yeah, that he won't happen. And again, I have an open offer. Just give me a reasonable number. Now, the last figure he gave me was $10,000. I believe that was the number. 10,000. Well, I'm not paying you $10,000 to play a 5-minute video. So that ain't gonna happen, bozo. So let's try to narrow your extravagance down to something a little more reasonable, so I don't have the right to call you a despicable coward, because that's all you are. Is a despicable, cheaty, conniving, slimy coward. All right, you're not a scientist. Scientists aren't afraid of arguments. Just a fact. If you're going to be a scientist, you have to defend your crap. You can't sit there and run away. I'm just going to say, praise Allah and then run. And that's all they do. Because they're just religious kooks. It's a fact. They let a bunch of religious kooks write the physics Bible. Okay? Leibniz, religious kook. Joule, still a religious kook. Bohr. The Bohr is the guy who said to Einstein, don't be telling God what he can't do. Pretty scary shit coming from a scientist. Alright, anyway. So, till the next time and such and so forth and whatnot. Sorry about all this entropy stuff, but just happened to be spontaneously what happened. Oh, that's right. It didn't happen spontaneously, did it? No, it was a cause and effect thing. A little chain, of linkage. So this became a subject. But it is a good illustration of how they even write laws that are mushy nonsense, and they just keep preaching them, even though it's almost too obvious that it's not happening. So they're saying something. This is like the 25 times the fuel to go 5 times as fast. It's obviously doesn't work. It obviously doesn't happen. The 8-pound bowling ball having twice the energy, yet no bowler in the universe uses one. It's obvious it doesn't work. It's not the truth, but we'll just keep preaching it anyway because we're scientists and we care about the truth. Yeah, bullshit. You're just mullahs preaching crap. Babble. Bullshit. So, till the next time and such. And so forth and whatnot. Cowards. Despicable cowards.